Good afternoon, welcome to, I was going to say welcome to the recent results session, but that would just wake you up. So welcome to the performance session. We have 3 talks this afternoon covering various elements of performance measurement, how the network behaves, and quality of service. The first speaker this afternoon will be Victor Oliver from UKERNA.
Thank you, Steve. Do you hear me? Okay. Good afternoon. I'm going to provide you with some information about the GeNet course development project, which started in quite a long time ago, in 2001. It's still ongoing, and hopefully it will be alive for another couple of years, and finally will result in some GeNet course production services, because currently we don't have course production services on GeNet. Quality of service course, as you know, is a technology which aims to compensate some negative effects of queuing on packet switched networks. It's generally queuing and queues, it's not so bad thing, but you know, it has some negative effects like such as delays, jitter, and loss. And of course, it's quite good technology to compensate these effects. But do we need a course at all on GeNet? It's a question because it's quite a hard question to answer, because in 2001, GeNet became a quite high-speed network with a very good backbone, which consists, still currently consists of 10 gigi core links and 2.5 gigi access links. So the question to deploy course or not to deploy, it's quite interesting. And the correct answer is not just yes or no, it's rather conditional yes and conditional no, because GeNet, as many large networks, is actually hierarchical multi-domain network which consists of at least 3 layers of hierarchy. Backbone, Super GeNet, currently it's Super GeNet 4, regional networks, and campus or site networks. And by using street lights colors, we can paint backbone by in green, because currently it's a well over-provisioned part of network, and we have average load like something like 10, 15, no more than 20%. It's a congestion-free zone. Regional networks we can paint by amber, because regional networks, some links can experience some congestion sometimes, and site campus networks are most suspicious parts of GeNet, because some links still 2 meg links, and the congestion can easily happen in campus networks. Well, having this in mind, and having in mind that volume of traffic still increasing, which can impact especially real-time and real-time services like such as voice over IP and video conferencing. So we decided, the GeNet community decided to start the GeNet course development project in 2001. Initially, it was just some initiative, course think tank. People decided to start or not to start this project, and just made some review what was going on then in course area. And formally, the GeNet course development project started in 2002, and you can see 4 main stages of this project. Most interesting and important last 2 ones, and configuring backbone and partner networks. For course support, it happened in 2003, and we did some large-scale testing across GENIC production. It was a real production network with some real application during the first half of 2004. It's a diagram of GENIC. Here, backbone, regional networks, and campus networks. You can ask me what for we deployed COS support on the GENIC backbone, because as I said, it's well over provisioned part of our network. The answer is just to obtain some real experience with COS configuring. It's one reason. And the second was just to show some proper patterns of routers configuration for COS support, because GENIC NOSC, probably the most experienced people in all networking areas, including COS. So last stage of our project so far. It's large-scale testing. 6 universities participated in this stage: Lancaster, Manchester University, Swansea, Southampton, Imperial College from London. Okay, 6 was not university, it was UKERNA itself. And we explored 3 classes of COS services. We explored IP premium for time-sensitive applications like video conference and voice over IP, the most elevated COS service. We explored less than best effort COS service, which is not elevated service because it's designed, initially it was a scavenger service of the Internet 2 community, and it's designed for elastic, for bulky grid, not only grid traffic, but it's not real-time traffic, it's very elastic traffic, which can be delivered in some background manner, just filling up gaps between best effort and IP premium. And of course, the best effort traffic remained for the rest of our applications. We deployed the DiffServ model, and there are different flavors of DiffServ model. We deployed some, probably the simplest form of DiffServ model is static destination unaware model, which means static means that all border routers were configured to allow or to accept some fixed limit of IP premium traffic. In our case, it was 5% of overall bandwidth of access links. And this acceptance was based not on destination of IP packets, just any destination is available according to this domain. The main aim or the main idea behind our testing was just to compare the behavior of real application on real production network when they were served like regular best effort traffic against the COS service like premium or less than best effort. And we used 2 kinds of comparison criteria. Subjective, when people carried out some tests, they just listened to each other by using IP phones and watched each other by video conferencing facilities, and they could evaluate the quality of service. And we used as well some objective measurement. We measured well-known COS metrics like round trip times, jitter and loss. And for this purpose, we deployed some partly centralized monitoring infrastructure which was based mainly on Cisco Service Assurance Agents SLA, which is piece of IS, this piece of software embedded in IS, which consists of SLA probe, which injects some small amount of traffic into a network, and the SLA responders, which just reflect these packets with timestamps, and the SLA probe have a possibility to measure delays and so on and so on. Our today chairman, Steve, was the main person who led this activity. So any questions about this monitoring infrastructure? It's for Steve. Here you can see an example, some typical example of our test bed or test scheme. We had some router which we wanted to test, and some interface or interfaces. Mostly it was only one interface which was to be congested, and this router was somewhere on Janet. We used applications, application generator. It was mostly Cisco voice over IP phone or Polycom or other probably companies' video conferencing facilities. As I said, we used SA responder and SA probe for measurement. We also tried to use other tools for measurement, just to compare results. Unfortunately, they were uncomparable. iPerf, it's open source software for measurement one-way delays, jitter, and loss. And to create some artificial load, we use rude traffic generators, which were also open source software. And because we had to carry out our test during so-called at-risk Janet periods, which are every Tuesday, I think, morning from 7 a.m. until 9 a.m., not to disrupt normal production services on Janet. So on top of natural load, we used some artificial load, and as I said, we used root traffic generators, at least 2 generators, just to congested output interface. And it's symbolize our measurement system. Some central database collected all results from SAA agents. Test results. They were quite encouraging, because in most cases we could watch that voice over IP applications and video conferencing applications benefited from IP premium service. At the same time, less than best effort service also received some small amount allocated bandwidth, which was mostly 3% of overall link bandwidth during quite severe best effort bursts. We observed also some peculiarities, but not so many. This is a quite typical graph, which it's just a snapshot of real-time graph. It was a test between UKERNA, IP premium test between UKERNA and Manchester. And this first burst, it was just trial of our tools, some tuning. And the second one was quite interesting, because we established a video conferencing session, and we established several voice over IP sessions. And the video conferencing traffic was served like best effort traffic, and at the same time voice over IP sessions were served like IP premium or expedited forwarding. And after we applied our artificial load, a lot of load, what we experienced, a big raise of best effort traffic delay, and even this light green is just best effort loss. But red line was IP premium, quite good result. IP premium slightly, we can see some slight increase of delay and no loss at all. And subjectively, we just observed that voice or IP session quality was very good, like before we applied the burst, best effort burst, but video conferencing picture just got frozen. And the third burst, we solved video conferencing and the voice over IP session, all sessions like IP premium, and subjectively we didn't notice any disruption. Another one is about less than best effort, and the upper graph is represents best effort behavior and bottom is less than best effort traffic. When we applied some burst of best effort, you can see the less than best effort traffic still received some allocated amount of bandwidth, a quite slight decrease of throughput, but not very damaging for less than best effort. Well, and probably the main unexpected result which we noticed was that window of cost benefits which we experienced was only when we applied a lot of artificial load. So when utilization was near 100%, so we watched and observed some disruption for best effort and some benefits for IP premium, which is not so obvious because, you know, it's quite a well-known dependence between utilization of network resources and some cost metrics, like, for example, delay in this case. And when we have, our traffic works in over-provisioned area, which is about 10 up to 20% of utilization. So normally no queues, no negative effects. And we expected that we would observe some negative effects when we apply about 50–60% of artificial load, but we didn't notice anything strange and no changes compared to over-provisioned area. And only we applied about 80–90% of load, but definitely and really watched some disruption for best effort and some benefits for IP premium. Why it happened, we still have to explore, and we hope to explore this during phase 2 of our project. And the possible, quite likely reason for this, we applied almost regular traffic, because root traffic generator easily produce regular traffic with fixed interpacket gaps, but it's quite difficult to generate bursty traffic. And these curves show that when your traffic is very regular, these negative effects take place only in this area. And if we have quite bursty traffic, probably we will notice something bad earlier when the utilization are about 50%. We are going to deploy during phase 2 of our project more sophisticated traffic generators like agianst boxes and probably something else. But we didn't have this possibility during phase 1 of our project. Okay, so currently we finished phase 1. We had some encouraging results, but definitely we still have a lot of job to do to convert our experience into some cost production services. So participants of the project decided to establish phase 2 of the project and define different cost service models based on the DiffServ model, and eventually produce something very close to the cost production services. And during phase 2 we are going to keep pace with agianst activity, because they have absolutely the same goal to establish end-to-end cost services across multi-domain academic environment. Now we are going to establish within GENIT community something like cost architecture group. It should happen, I think, this summer or probably this autumn, which will consist of several working groups. We would like to explore inside of this working group policy management different flavors of DiffServ model, not only static destination unaware, but as well dynamic destination aware model, which currently is being explored inside of agianst activity, and would like to establish more scalable monitoring system and explore new applications which could benefit from costs, such as real-time sensitive grid applications, and go further to the periphery of our network, working with schools and further education institutions which have a low bandwidth connection, and eventually explore some inter-working issues, costs against, not against, together with IPv6, multicast, firewalls, and so on and so on. Well, finally, I'd like to tell about which models, quite on the quite high level explanation, which types of DiffServ models we are going to explore during phase 2. Classification is quite difficult thing to classify DiffServ models, but at least 3 quite important factors exist. It's destination awareness of your cost services, static versus dynamic reservation, and trust relationships between domains. This is what we deployed during phase 1. It's static DiffServ model. I showed this one. Let's skip this. This very good model in terms of scalability, flexibility, maintainability, but it has one innate flaw. It can't provide some quantitative guarantees in terms of probability of good cost service, because this model doesn't trace flows, traffic flows inside of your domain, and the clash of flows in some output interface, it's quite legitimate event. It's allowed. So applicability of this model is quite limited. We can deploy it for very few well-known sources of IP premium traffic, and it's not a model for when you have thousands of users. Another one model, it's a dynamic destination aware DiffServ model with bandwidth brokering. It's quite good model. Every domain has a bandwidth broker, which is software which sits somewhere not inside of routers. It's mostly some server. And this bandwidth broker accepts requests from end users and tries to understand availability of resources, mostly bandwidth. Quite good, and but this model has also quite obvious restriction. It's not very scalable because it tries to trace every individual flow in your domain. And for high-level domains, it's not very good. And probably some hybrid model when high-level domains like our Super GENIT or agianst, for example, These domains should trust in some aspect to low-level domains in terms of admission control of individual flows. So high-level domain can remain static configured, and only low-level domains in this case will carry on the admission control of every individual flow. Probably it will be much better in terms of scalability. We still should explore this question. Mostly that's all what I wanted to tell you. So you can find quite detailed information about current state of the GeNet course development project if you go to GeNet website and find course pages. Thank you very much.
Thank you, Victor. I can feel some questions, but are there any pressing issues that you would like to raise with Victor now? I think these are questions that need to be taking place over a few beers later on this evening. Thank you very much,
Absolutely.
Victor. Our second talk this afternoon, looking more at the more into the monitoring aspect. Athanasios Thoutsis. Thank you. You're getting lessons in pronunciation. Just a reminder, when you get to the conference dinner venue this evening, keep an eye open for the terrain signs and follow the arrows or the hands of people pointing you in certain directions, just to make it easy to get to the venue. How you get out of the venue and back home is your own problem.
Greetings. This presentation is about SLA monitoring with the Nagios tool. This project was developed by the National Technical University of Athens in Greece on behalf of the Greek Research Network as a part of our project to develop a system that can monitor service level agreements in the NREN of Greece. Okay. We're going to have a little introduction in service level monitoring. Then we're going to describe the design and architecture of our system. We're going to have a small talk about the implementation, draw some useful conclusions, and if there is time in the end, there's going to be a little demonstration of the system. Okay, first, let's make a short introduction. Yesterday's applications were not that dependent on crucial network characteristics, but today it is a whole different matter because there are applications like IP telephony or video on demand or video conferences or internet radio, those sorts of things that are heavily dependent on characteristics such as the RTT, the packet round trip time between two peers, also the variance of the one-way delay of packets, which is known as packet jitter, and of course the percentage of packets that are lost during a conversation, and of course the one-way delay itself. So it is logical to define a network service based on these network intrinsic characteristics. So the network may be functioning and there may not be any sort of malfunction, but the service we are getting may not be adequate for certain applications. So it is logical to define service level agreements based on these intrinsic qualities of the network. So how do we go about monitoring SLAs? Of course, it is a question of monitoring the characteristics that I just mentioned. The steps that we would follow if we generally wanted to monitor an SLA would to spread probes across the network. Those probes would execute the measurements. Data should then be collected and then processed. These two steps can be interchangeable. I mean, there may be some sort of processing even before the collection. And of course, the data can then be stored appropriately and be presented possibly with a way that integrates well into an organization's current network management system. Of paramount importance is that the measurements themselves are as accurate as possible. It is really a question of accuracy of time measurement. Okay, today with our super fast networks, the measurements must be millisecond accurate. And of course, if we are talking about one-way delays or jitters, there should be enough synchronization between the two peers that the measurement must be accurate enough. So this can be done either using the network time protocol or even there are GPL-assisted techniques. Of course, the measurements can be enhanced by using kernels that have real-time capabilities. And of course, like it was said in a previous presentation, in the previous session, there are also special pieces of hardware that can timestamp the packet even before it reaches the processor of the system. Okay, the design we draw, we felt that it should be dictated by the following design goals. First, like we said, accuracy of measurements is of paramount importance. The other two factors are the deployment and the installation of probes in the network. There are several techniques that use dedicated machines to monitor the characteristics of a network. These approaches can be expensive in terms of installation costs, equipment costs. So if it was possible, we wanted in the initial phase to save this effort. Of course, the operation of the system would have to be as simplified as possible to minimize the burden on the network administrators. The communication between the components of the system themselves should be efficient enough and not place a burden on the traffic of the network. Of course, a production network has problems, there are malfunctions, there are outages. This system should be resilient to outages, so the measurements have to eventually reach the system, even if it is not done immediately. And of course, we have to use standards compliant parts and make appropriate choices so that the system should be modular enough so in order for us to be able to extend it as we see fit in the future. This is the general architecture of the system. The probes themselves are installed inside the routers of the network and they execute measurements amongst themselves. The collector gathers the data using SNMP, and then after some sort of processing, the data ends up in the database where all the measurements are stored. Then the data is available for our Nagios network management system to query it and produce results about the SLA status of our network. Based on these results, there can be mail alerts, pages, or even we can check the results via the Nagios web interface. Of course, there can be other forms in which the data can be accessed. perhaps some sort of web service or XML schema can be used so that other applications can access the data directly instead of going through the Nagios interface. For the probe implementation, since all our routers on our network are based on Cisco equipment, we have used the Cisco Service Assurance Agent, which is a standard feature of iOS. SAA works like this. In effect, you define functional units which are probes, and then the probes get scheduled in regular time intervals where they execute certain types of measurements. There are many sorts of measurements that can be done by SAA. In fact, the system, I think, is extensible so that new measurements can be defined, but we felt that the echo and the jitter probe are the ones that we need to measure all the intrinsic characteristics that we mentioned earlier. The system itself has the capability to aggregate the measurements so that we don't have to query and collect each measurement by itself, but the measurements are grouped into hourly groups and then collected by our collector. The SAA NIB can keep the hourly sets for each probe for up to 24 hours back, so we have the capability to withstand network outages and come back later when the outage has finished and collect the data. The data collector gathers all the measurement data from the SAA devices, which are the routers of the network, and stores it in a database. Of course, the data is available through the Service Assurance Agent NIB, and so the collector essentially, SNMP works the MIB and processes the data and then stores it into the database. The data collector has some interesting features. For example, reloads or reasons for which the router is unavailable can be detected, and the data collector returns again shortly after to collect the missing measurements. Of course, if we introduce new probes into the router, the collector detects them automatically and then inserts appropriate entries into the database. Of course, these collectors can be used in some sort of parallel, so we can have many instances of the data collector working independently from each other. So this could allow us some sort of redundancy to our system. The schema of the database, we have used a database instead of a RRD tool or something like this, as we will show later, to have the flexibility to introduce any queries we might want. Each probe is identified by the router which it resides in, and the tag, which is the name which we have given it. So each probe can be uniquely defined within our network by this pair. There is, of course, the tag registry where holds each pair of these and all the other interesting probe characteristics. The measurements themselves are stored inside the echo probes table, which stores results from probes which are of echo type. This is essentially round-trip measurements. And there is the jitter probes table, which stores results from the jitter measurements. Both tables are indexed by the probe ID and by the time the measurement was done. So the database can be indexed by those two, by this pair. So large queries that span even almost a year can be done and be executed fairly quickly. About Nagios. Nagios, as you probably know, is a service monitoring tool, network and service monitoring tool. There's the concept of services which are associated with hosts. The information from the Nagios tool is available through either web interface. There are also mail alerts. There are cell phone pages, that sorts of things. And what's really interesting about Nagios is that the architecture is really extensible, so that it can easily integrate new service checks. Because each service check is essentially a plugin, which is an external application which gets executed and is designed to check for if a specific service functions. So it is the way that the plugin communicates with the Nagios main application is well defined. So it is really easy to introduce new plugins, write new plugins that use this rigidly defined interface with the main application. This is exactly what we have done. We have wrote our own Nagios plugin, which is capable of reading from the database, querying the data, and then compare it with some predefined metrics which we have done, and report the results to us. The metrics themselves are not only those intrinsic characteristics that we introduced earlier, but the queries can be complex enough to calculate things like the downtime of a certain link, or of course it can check if the jitter has exceeded a certain tolerable limit for example, voice over IP operation. The queries that were used in the sense of time can be for the last hour, for the last day, last week, and so on. But we can essentially make any query that we like. For example, we can make queries that are based on calendar periods. For example, I can query from the 1st of June until the 8th of June, which is now. Of course, I can query for only work hours or exclude weekends and so on. A few words about the implementation specifics. So, how did we, what SAA probe settings did we use? First, we use, like I said, we use only two types of probes, which is the ICMP echo, this is essentially the ping probe, and a jitter probe. Of course, for jitter measurements to be made, not only the router that is running the probe should have SAA should have the SAA capability, but of course the other end must be SAA enabled also to make the measurement. So the other peer has to run Cisco IOS and have the SAA responder feature available. We deploy SAA probes to all the routers in the network, and we have each router ping and jitter all the other routers inside the in our network. The probe configuration itself is a measurement per minute, and each measurement is 10 1 kilobit packets for each minute. The bulk storage is tuned to 3 hours, so even an outage that is 2.5 hours can be overcome, and we can come back later and collect the results. Of course, this gives us the capability to use the same configuration in all the routers of the network. So we can make a configuration which will be deployed everywhere, and we install it to all the machines simultaneously using TFTP. Some words about the collector. The collector essentially can be run can be installed inside the cron tab of a machine and be run at regular intervals. The collector discovers the available probes and updates the tag registry accordingly. And and of course, the sets that have not been inserted yet are marked, and they are inserted in the next run. Okay. Now, the Nagios plugin is essentially very simple. It is a system that queries the database and then calculates the metric that we are interested in and compares it to the threshold like we said earlier. It is noteworthy that we use the same plugin for echo and jitter queries, as it is just a matter of executing a different query. The time queries and the metric queries are configurable externally, so we always use the same plugin. Okay, now some conclusions. The fact that we didn't use dedicated machines to execute the probes guaranteed that it was extremely easy, like we said, by using TFTP, to deploy the probes, and also the administration had minimum overhead. Of course, there was Nagios, which was already there, and so the administrators had the added benefit of using a system which they were already familiar with. And even the whole operation of the system is relatively low, not only on network burden, but also on the burden of the machines, because the system is very light as to the fact that all the measurements are grouped by our sets, so we don't have to collect each measurement in itself. Of course, there were there were many SAA bugs which we had to work around or notify Cisco and open some cases, but overall the system works quite good. Some future ideas are to replace the service assurance agent and use the MIBs from the distributed management, like the ping MIB, or and of course other programs who would like to use the system could have the measurements available through the web service. This is essentially something similar to the thing that Nicolas said in the earlier presentation. The measurements can be made available possibly using the network management working group from the Global Grid Forum, the appropriate XML schema. That would be it. I think we have time to make a short. For example, let's take the downtime monitors of the SAA probes on our system, on our network, excuse me. Takes a little time. So let's take the monthly downtime service level agreement. As we can see, the system checks the last 30 days for each of the probes that is stored and available inside the database. For two of our links, there's some sort of warning. This should be an outage that happened, I think, today or yesterday. These two warnings are sent also via email to the administrators. And so the administrators have a handy interface, so where they can go and check whether everything is okay on the system and where whether the SLA for the last 30 days is breached. As we have seen, there are SLAs for various time periods, and of course, each of them has a different downtime threshold. For example, we can tolerate a downtime, say, for 5 minutes per day, and also we can tolerate a downtime of 2 hours per month, for example. That's about it. We have time for questions, right?
Yes.
You're going to be making these questions. Okay, it was quite. There were similarities with with what you did. I don't know if this was a case of what industrial espionage.
It's very well. We built a very similar system for the quality of service trial, but you can actually do it per class of service as well as just doing measurements, which is what we used for it. So it's good. We can just thank Athanasios. Anybody have any questions for the moment? They're all stunned. That's excellent. In that case, thank you very much. And I keep walking away from the microphone. Our final speaker of the afternoon, Michal Przybylski from PSNC, who has been fairly heavily involved in the organisation of most of this conference. So the fact that he actually managed to find time to write a presentation whatsoever is quite impressive. Do you want the radio mic, or are you going to?
Yeah, I take that one.
Yeah, okay.
So, by the way, thank you, Steve, for warm welcome. Thank you for learning my name properly. And I still discovered marks and stuff. Is that too loud, or is it okay? Well, the presentation is the result of our activities linked to the standardization process of the IETF reordering draft metrics. There are 2 drafts, draft Yaya-Suyama and reordering measurement. And we have cooperated with IETF a little bit, and we have tested what they propose, and we have found some interesting, I think, observations, and I want to share it today. So I'm going to say a little bit what is packet reordering, what are the sources of packet reordering, and if there is a need to worry. First of all, there were several articles before that one saying that reordering is not pathological network behavior. In fact, it's not, because IP network guarantees only it doesn't guarantee, but it does not guarantee as well a packet order. It just says something about delivery of IP packets. It doesn't say anything about the order. So everybody using IP network should assume that there is packet reordering, and that should be natural. But it seems that well, people do not assume that. People assume that they live in the world where the conditions are always very good. There is no reordering, and they engineer the protocols like TCP in such a way that if there's reordering, they do not perform. So you have this strange situation when whenever we test the bandwidth, whatever tool, except for the TCP, and then everything goes fine. All the packets are there. Everything is delivered, 0 packet loss, and then TCP streams performs on 1/20 of the available bandwidth. And we try to find out why, and then we see that there are losses in TCP, but if packet is reordered more than 3 places, then TCP will consider it lost. So this is the fault of TCP, not of the network. Network is fine. Well, the last sentence here. Normal conditions, normal network conditions, something that everyone considers normal network conditions, is in fact right now extremely rare case, what we found during our observations. In extremely rare case, there is no reordering in the network. So in general network, there's reordering almost always. The extent is just different. Well, a little bit about the metrics. What was packet reordering before? Was a percentage of packets. Well, if we take, for example, this stream of packets, 10 packets, sent properly from the source to the destination. And then we see that 4, 5, and 6 overtook 3, and 10 and 9 overtook 8, which is underlined here. Then we can say two things. First of all, 30% of packets is reordered because some packets are late. But somebody else can say packets are reordered, but it's 50% of packets are reordered because some packets are early. Well, from that example, we could deliver a lot of data, but with the current approach of percentage reordering, we cannot. I'll show you why later. Another example. 50% of packets here are reordered. Every 2 packets are reordered. But according to the theory of TCP, this will not affect TCP stream because TCP should cope well with 2 reordered packets. So if every 2 packets are reordered, this is my theory only, I didn't check that. In reality, because it's extremely difficult to check that in reality because you would have to engineer your network somehow. But at least the theory says that TCP should cope with it. So TCP is able to just restore order in 2 or 3 packets depending on implementation. There are also reordering robust TCP implementation that can deal with much more reordering, but I'm talking about standards one now. So our measurements would say we have 50% of packet reordering, very bad situation in the network. But our TCP stream should behave perfectly, should have a high bandwidth. While in this example, when you have 30% of packet reordering, or imagine just 1 packet reordered by 3 positions, this packet would be considered lost, and the TCP would not perform. So the percentage measurement is not comparable. You can have different streams, differently reordered, and you cannot compare it. There are new metrics without IETF. I think they are competing now. There's draft Yasuyama reorder density, and they talk a little bit about reorder buffer occupancy density, which is kind of histogram showing how much buffers you need to have in your application to deal with the reordering. So this is an example of the measurements in agianst. You can see that some 5% of packets are reordered. In fact, and you need one buffer space, one packet, whatever. But you can also see that at position 8, there's also something. It means some packets were reordered by 8 positions, and you have to keep first 7 or 8 packets just before you find the right one, and before orders arrive, and you can restore the order. So that says something a little bit about how you should tune your application. Well, there's another draft, IETF IPPM reordering, by a competitive team of authors who are trying to look at also at the buffer, but also try to show it in the time space. So they have the extent of reordering, which is almost the same as reordering density, but already in the document they show it as for every single packet they show the extent of reordering, where you can see how many packets every single packet was reordered. And there are derivatives like how many bytes you have to keep in your buffer in order to restore the order, or how much time you have to have in your buffers. So how much extra delay you will get in your application if you do reorder buffers. So these are the metrics. There are new metrics, and I think they are much more informative because with that one you can see what's happening in the time, and you can see microscopic phenomenons where you can see, for example, periodic high reordering values, or you can see it's basically if you compare these two, for example, that one and that one, you might see that, for example, for the position around 101, you had 6 packets, which corresponds to 140 bytes, which means the small packets are reordered much more often. That's easy to notice, and you can also notice that from looking at the particular records of the traffic flow, but that's maybe easier here. You can find it very quickly. Why is packet reordering in the networks? Because the networks are done in a parallel way. So I'll just try to extend that later. Also, we have network faults. if the route is flapping, if you have some BGP problems or any other routing problems, then some packets might go one way, some packets another way, and then we have reordering. We can have improper configuration. Somebody tries to make our network better, apply some maybe classes of service, and instead of, that's similar to the special QoS performance configuration. If you remark your packet, if it does not conform to the agreed SLA, for example, the queue size, then if you remark it and send us a best effort, in case of premium IP service, it will go in with the lower priority. So it might happen that some packets will be remarked and will go slower than other packets which are considered as premium IP, for example. And then you can see reordering in the overall stream. Probably it would be better to drop these packets, not to cause reordering, because if they come too late, there's no point at all. If they come too late, they're unusable. Well, also faulty software. I read somewhere about the implementation of routers. Somebody wanted to improve behavior of routers during congestion and the control of TCP protocol. So if there was congestion, the new packets were forwarded to the input queue, but they were scattered in the input queue. So some packets were removed from the input queue, and the new packets were scattered. So it makes impression that every stream is a little bit affected, but it was just faulty software. I'm going to speak a little bit more about parallelism because that's I'm most familiar with. So we have link bundling. For example, you might buy Ethernet switch and use 3 gigabit Ethernet ports to achieve 3 gigabit per second. And depending on the routine, queuing routine or scheduling routine, you will have reordering or not, or you will have different limitations. There's also load balancing. So for example, you can use two paths or 2 links to balance your load because of many different reasons. But anyway, there's again queuing regime that you can apply over there that causes reordering. And also right now, with the high progress of technology and the desire to have the fastest interfaces ever, vendors are using old chassis and they put new cards or new processors. And in fact, if they want to go to 10 gig or something like this, they reuse components from 2.5 gig circuits. Or if they reuse components from 1 gig circuits to get to 10 gigs. And this way they introduce parallelism internally. And every queue of that, every internal queue has its own life and treats packets differently. So it might cause reordering, as you will see in the example. So the queuing regime, if you have many internal queues or parallel links, you can have per packet round robin. So every incoming packet is treated by round robin. So first packet goes to the first interface, second to second, and so on. And if you have asynchronous queues, then the first packet, which is probably long, and the second packet, which goes to another queue and is much shorter, will be processed much faster. And this way, the shorter packet will overtake the longer one because of processing time in the queue. Well, you can also have workarounds to round robin, which was introduced by Juniper. I'll talk a little bit later about it, which is constant packet processing time. So that's a kind of assurance that if packets goes to the first queue first, it will leave first queue first, and then the second packet will leave as the second. Well, it doesn't seem to work well in the old devices, but the new devices they do sort of that things. I think it's also on the cost of the speed of the overall solution, because for example, you have to wait. You process a small packet, but still you have to wait for the long one to be assembled, and that is like slowing down your network. And you can also have per flow scheduling, which is most probably will preserve the order, but the queue capacity will be the limiting factor. Imagine you have 10 gigabit interface composed of 10 1 gigabit queues. So if you do per flow, your flow would not be higher than 1 queue, because you can forward the flow only to 1 queue. You cannot do it to 2. We have that problem in our network. So just practical example. If you have 10 gigabit interface with 4 queues of 2.5 gigabits, And then you have this per flow regime, which you applied because you do not want to have reordering. And assume that you have interface load of 4 gigabit per second. So you have 40% load. And this is mix of internet traffic. So money flows, point-to-point flows, very short, so thousands or millions of flows on that interface. So if you use per flow regime, then theoretical flow size would be 2.5 gigabits, which is something probably that everyone could agree with. Okay, nobody needs such streams right now. But if you assume that you have 4 gigabits load, and this is statistically, say, equally distributed in these queues, it means that every queue has already 1 gigabit load, because there are 4 queues and you have 4 gigabits of traffic. It means that a new stream, which will come to the router or whatever, switch interface, will hit the queue which has total capacity of 2.5 gig, and there will be 1 gigabit of traffic in the background. So even though you have theoretically 6 gigabit of free space in the interface, your flow would not be higher than 1.5 gigabit per second, and you will hit congestion condition. So that's something you should consider when you buy new equipment. I think right now we have seen it with 10 gigabit per second. Now this technology is mature, but we'll see it with 40, I guess, because they will use 4 times 10 gigabit to deliver you 40 gigabits, and then we have the same situation. So we know there is reordering in Juniper M160, which we found out during many years ago in the second project, and that's from light reading. They found out that there was no proper reordering metrics. Then they only were able to measure percentage of the packet which were reordered. So only the load was over 73%. Then they found some reordering there, as on the slides, right? But in agianst, what Tiziana tested, at least she subscribed to this, she signed this document with her own name. She says that there was packet reordering during LBE testing, where they configured different classes of service, and there were different priorities to less than best effort and best effort queues, and then packet reordering was affecting that. And I found out that chart, which shows that if you are close to the maximum interface capacity, then you might have 90% of packet reordering. It shouldn't happen, but it happens. So you have to take that into account. This is just 2 slides taken from the large paper. So maybe if you read that paper, there will be more information just to show you that things like that happen. Well, in our network that we have in Poland, we have Black Diamond 6808 switches. They were first affordable 10 gigabit Ethernet switches that we could buy at the time when we were creating our network. And we found out, and probably we knew before, but we did not realize the danger, that there are new interfaces in the old architecture. Because originally these switches were designed to serve 8 gigabit ports per card. Therefore, they have the backplane connection made with 8 times 1 gigabit queue, or like 1 gigabit whatever interface. So right now, our 10 gigabit Ethernet card is served by 8 queues, which effectively limits flow size on empty switch to 1 gigabit per second. And right now we have 4 gigabits or 5 gigabits of load in the network. So the maximum flow size, which is not reordered, in our case is 500 megs, which makes our network unusable for VLBI or CERN. And we have to find solution quick. And there's no workaround for this switch. Unlike in Juniper, you could manipulate with the weights, you could try to do some workarounds. But in here, you can't do anything. We can either enable round robin per packet, so we have large reordering, TCP is not performing, and VLBI people are unhappy. Or we can have per flow regime with 500 megs per queue, which also makes VLBI people unhappy. So we have to change these devices. Well, I have a few words about measurements. If you might want to measure 2 things in your network. First of all, I would strongly discourage from using pings or trace routes or the ICMP packets. because they might be treated specially by routers. Routers might have some limitations, and I think the best idea to measure reordering and also many other parameters is to use UDP packets shaped as the application that you want to use in the network. If you want to stream something, do it locally, capture test, capture the trace, see what packets are there, create a packet trace for UDP generator, send this packet, see what's the reordering. Then you will know what to do. You will know what buffers to install, how to compensate that. Otherwise, with the ICMP packets or something like that, you might not get it. Then you might also want to see how your network behaves. So for this purpose, you cannot send for reordering probes which are like spaced second by second, but you have to do this in a short burst, because reordering will only happen if you have 2 packets arriving at the interface with very short inter-packet gap, so they are very close to each other, because only then they can overtake each other. If you send packets, if you want to measure everything and you send probes every second, then you have 0 reordering. You will have to send the line speed. You always send line speed for reordering. So, and if you want to see what is the best your network can do, best, I mean the biggest reordering, just send long bursts of long packets followed by long bursts of short packets. And we see short packets overtaking the long ones. Well, we did try to find out the network fingerprint of giant network, sending at 100 megabits per second from several machines in Europe, where 10 long and 10 short packets were high speed. And the results were as follows. Again, this is typical result for every pair of hosts that we tested. So you can see 85% of the packets were okay, but some 5% were reordered by 1 position, and maybe some 2% by 4 positions. So 2% of packets were lost for TCP, or maybe this 3 position reordering was also lost. So 3 or 5% packet lost. That's a packet loss for TCP application in giant, right? But you don't see packet loss as a packet loss in ping probes. You will never notice that, but only if you send the high streams. Well, just to show you the practical application that behaves like that or can suffer from reordering, we have noticed that several streaming applications, they are highly fragile or vulnerable to reordering, because they assemble voice packet. So they take a few milliseconds of voice, they create digital data, and they put that in the packets. So if, for example, you have 5 kilobytes, say 5,000 bytes of data, then probably it fits in 3 packets, and then you have maybe 500 bytes long packet, the last one, Ethernet frame, right? Or you might have, say, 20 bytes or 60 bytes or 140 byte packet at the end. So you have 3 long packets and 1 short. And then you look at the destination, and the first packet you receive is the last one of this packet, because 1 second of voice can have like 5 kilo or something like that, kilobytes of data. So once in a second, for a very short period of second, you send 5 packets, 4 long, 1 short. And you do that every second if you're streaming like this, because that's the way the codec works. It assembles all the data and then creates suddenly a packet and sends burst of frames. And then at the end, you're receiving the last frame and then the remaining 4. The 4 in the right order, but the last one just overtaking that. So, well, the question's open. I just tried to write, to show you a little bit of what we found. And I think the reordering is there. The reordering will be there. Even if we get to 40 gigabits and even 160, there will be limitations in the processors and we'll have reordering. Well, none of the vendors will tell you about it until you ask. Until you explicitly ask. If you buy on the switch or router, you have to ask in the tender, otherwise they tell you everything's okay. And then you find out when you try to use your application. Well, most of the old applications using TCP are probably vulnerable. I think they are because I show you the results of reordering measurement. So there are many packets that are reordered more than 3 positions or 2-3 positions, which is bad for TCP. Well, we shall look for new reordering resistant protocols. And also, important thing is that reordering happens only in this microscopic scale. So you got microbursts which are vulnerable to reordering. If you have, you shouldn't think that if you have slow application, generally slow, it doesn't send much data, it will not be vulnerable. It might be because it sends data in short bursts, which are very fragile in that network. And yeah, large flows, if we have reordering, large flows are extremely affected. Especially if you look at the TCP, it takes hours to saturate. If you have a loss-free network, the TCP will take hours until it gets to 10 gig or something like that, and you lose one packet and it goes by half. So they're very much affected. I think to deal with the reordering, you have to understand the network, understand the application, and you have to craft your application carefully. And that's the message. Thank you.
I'd just like to thank Michal for pointing out that our networks are even more strange than we always thought they were. And I think one of the things that through the monitoring processes we're seeing more and more is the more closely that we look at these networks in the millisecond or microsecond detail, the stranger it is. And unfortunately, some of this stuff does seem to affect applications, which is the worrying part, whereas in reality it shouldn't, of course. Does anybody have any questions for Michal or for any of our... Do we have a wandering microphone? There's one over here. There's two. Can you just put your hand back up a second?
Have you already discovered any protocol for the new application to use in order to avoid reordering?
Well, there is a reordering resilient TCP, something like that. We have not tested it yet, but well, it's probably you have to.
Where is it implemented? I mean, in what operating systems?
Like probably for Linux. All the new protocols like that are available only in the open source. So you have to look for Linux, and this is, I think, is TCP-RR, something like that. That's called. We haven't tested it yet. I know.
It's
only
in the form of the kernel patch, right?
I think so. Yeah.
Okay, thank you.
You always have to patch the kernel, and don't expect Windows to be able to help you in that.
Yeah, sure. Yeah.
When you tested with TCP streams, you didn't test reordering with TCP? Oh no, okay. So I have no question.
No, I just say we only tested with UDP streams pretending to be TCP streams, but not without any window mechanism, right? So we're just capturing local traffic from two sides. For example, we're testing from one PC here to one PC here. We capture ethereal just to see how it would be if they were very close and with a good network. And then we're just sending the same stream across the wide area network with a constant speed, right? Like with the same speed, exactly the same spacing and the same size of packets. So this way I think we should also have some kind of very detailed TCP implementation to see what's going on at TCP level, also to understand better. At least we only look at the reordering.
Yeah, in fact, in the results that you have shown in the graph in your presentation, when we did the data test, we were injecting UDP traffic through smart bit boxes, and we had additional TCP traffic running between test machines and the POPs. And at that time, really, the TCP performance, even if we were marking data traffic as IP premium, was really going very, very, very bad. We were not really capable of understanding if that TCP performance problem was due to reordering, which was indeed that one, so it was huge, or rather a problem in the stack, in the TCP stack on the machine, or rather in the switch which was connecting the machine to to the router. And it was even very difficult to measure the amount of reordering that our TCP traffic was experiencing, because typically what we did was just running TCP dump sessions and then analyze the data. But then we had the low-end machines, and it turned out that the TCP dump was missing packets, so we couldn't really understand or quantify the amount of reordering experienced. We know that, for example, tools such as TCP trace can estimate, well, tell you if you are experiencing reordering or not, but cannot really quantify that. So I was asking, maybe anybody knows in the audience, if there are tools that you can use to estimate that. That would be greatly useful, I think.
Like heavily, I think you need heavily monitored TCP stack, right? Something like TCP stack that will tell you what's happening, like window size, lost packet, drop packet, whatever, right? Something like that.
Just maybe a dump mechanism to keep track of the TCP packets, and then we would need a tool that
just a network probe
estimates the reordering from a dump file. That would be sufficient.
Any other questions or comments? In that case, can we thank PSNC for the facilities and also our speakers? And we look forward to seeing you all this evening for the conference dinner. Thank you.